This is a lecture on the confidence intervals for the mean of the populations. So as we know that sometimes when we need to estimate a population parameters, for example, you can talk about we want to estimate the mean of the populations or the standard deviations of the population, for example. Then most of the times you want to collect a sample, right? And you use the sample statistics to estimate the population's parameter. However, the less error makes for a better estimate for sure. And knowing the margin of error, especially the precisions of your estimate, is important because it gives you the context to the estimated population parameter. Additionally, you can use the margin of error to construct a confidence interval, which bounds the population parameter with some level of confidence. So let's remind us what is a population parameter, right? Population parameter is a variable that represents a population characteristic, such as a population mean or population standard deviations. And a point estimate is a single value estimate for a population parameter. For an example, we were talking about the normal distributions. If the population is normally distributed, then the sampling distributions is also normal. And then you can use the mean of the sample distributions to estimate the mean of the populations. So the mean of the sample distributions is a point estimate for the mean of the populations. Unbiased estimator. So an unbiased estimator is an estimator, right? It's a point estimate or an estimator that does not underestimate or overestimate the population parameter. That means you can use that estimator to estimate a population mean or a population parameter without a lot of without big errors. So the most for example, in chapter 5, we learned that as the sample size increases, the mean of the sample approximates the mean of the populations. So then the most unbiased point estimate of the population mean is a sample means X bar when the sample size is big enough. What is an interval estimate? So an interval estimate is just the range of values. It's an interval, right? That containing infinite many points. And this interval here is used to estimate a population mean parameter, which means using this interval, you hope that you will capture the population mean that is inside this interval, in between this interval. Okay, so if this is the population mean, then you hope that once you come up with an interval estimate, the population mean, the population parameter that you're trying to estimate is inside this interval. Then what is the level of confidence? So the level of confidence is a probability that the interval estimate contains the population parameter, assuming that the estimation process is repeated a large number of times. So let's look at let's look at a normal distributions, right? So if you have a variable that is normally distributed, if the populations of the variable of the population is normally distributed, and then if you want to set up a level of confidence of, let's say, 95%. So C equals 0.95, right? that means with 95% of confidence, right? That means the probability that the interval estimate will contain the population mean. So if the distributions is normal, then this should be the mu, right? Mu is the population mean. And then you will construct your confidence interval that will capture the 95% of the populations. The 95% of the populations, and then this interval here, from this point, let's say the lower bound and the upper bound, right? So the lower bound and the upper bound of your confidence interval will capture the population mean and also the probabilities here under this area is about 95%. All right. So that's the level of confidence. The probability is that the interval estimates contains the population mean, right? Assuming that you will repeat the process, like the estimating process, a large number of times. Once we have the level of confidence, then we can talk about the critical values. So the critical values are the values that separate sample statistics that are probable from the sample statistic and that are improbable or unusual. So I would say the critical values, if you have, this is a normal distribution. If you have a standard normal distributions, okay, this is a standard normal distribution. Then the mean is, of course, 0, right? And again, the critical values are the values that associates with the level of confidence. It's separating the probable statistics, sample statistics, with the improbable sample statistics. So if you have a, again, this is we're still using the level of confidence is 95%, right? 95%, which means the probabilities from this point to this point is about 95%. And the critical values are these values right here. Okay, these are critical values. And then as you know that if we're using a standard normal distributions and if we given a probability, then we can find the z values, right? And in this case, in the case when you can use a z value or the z table, critical values are the z values that corresponds to this probability, which is the level of confidence. So the critical values and level of confidence are associated with each other directly. All right. And again, we're going to use level of confidence and critical values in order to construct an interval estimate. An interval estimate too, and then we use the interval estimate to capture the population's parameter, the population parameter that we're looking to estimate. Again, we're hoping to capture it with some level of confidence. All right. And the last things, like the last definitions, is sample error. So what is sample error? Actually, sample error is just the difference between the point estimate and the actual parameter value. It's a difference between the point estimate that you found from your sample with the actual parameter value. We always gonna have a sample error if we collecting a sample to estimate a parameter population, a population parameter. In realistic, we always have a sample, but with good practice, we want to reduce the sample error. We want to have as small as a sample error as we could. Okay. And in the following lectures, we will learn how to reduce sample error. We will have some criteria that we can use in order to help reduce the sample error. So once the sample error are reduced to a small value, we are better at estimating the population parameter due to the small sample error. All right, so this is an introductions about some terminologies of what we're going to use in order to construct a confidence interval for the population mean. Okay, when sigma is unknown, again, sigma is the population standard deviations. Now, how can we find the margin of error? How can we estimate, or how can we construct the margin of error? So given a confidence interval, so you have a certain confidence interval that you want to start with. Your confidence interval can be C equals to 90, right? C equals to 90%, 95%, or 99%, or could be just 80%. So there's are different levels of confidence that you can use for your study. So once you have a confidence interval, then the margin of error E is the greatest possible distance between the point estimate and the value of the parameter that is estimating. Okay, so you constructing marginal error, you calculating the marginal error, which is the greatest possible distance between the point estimate that you're using to estimate the actual and the actual value of the parameter, the population parameter that you're trying to estimate. All right. In other words, this is just the greatest sample error that you wish to have. So the marginal error is denoted using E, and is equals to ZC times 2 the standard deviations of the sampling distributions. Okay, and it's equals to ZC times 2 sigma divided by square root n, because the relation between standard deviations of the sampling distributions and the standard deviation of the populations is this, as we learn in chapter 5, right? When we talk about sampling distributions, when your sampling distributions is normally distributed, then this is the relations between the sampling distributions, standard deviations, and the population standard deviations. Okay, what is ZC? ZC here is a Z value that associates with C, which is the confidence, the level of confidence. And ZC here is actually the critical value. Right, the critical value that associates with the level of confidence C. Okay. So you can come up with, you can use this formula to find the marginal error E with the following conditions. First, sigma is unknown, which is you have to have the informations of your populations and deviations. Second, the sample is random. You have to pick a random sample. Third, the populations is either normally distributed or the sample size has to be at least 30. Okay, so the three conditions have to meet in order to use this formula to find the marginal error with a given level of confidence C. So let's do some example. Example number 1. Find the marginal error for the values C, sigma, and n given samples are randomly selected. Okay. C is 0.95, sigma is 5.2, n is 30. What is E? So using the formula, and we know that the samples are randomly selected. We know that sigma is unknown, sigma is known, and we know that the sample size is 30. So the three conditions satisfied. So then we can go ahead and use this formula. So formula is E is equal to ZC, right, times sigma divided by square root of n. And then this is the point where you ask, how can you find ZC? Given C is 0.95, okay? So you have a standard normal distributions. If you have the probabilities, then you can find these two critical values here, right? And you have a negative values and a positive value. In finding marginal error, you just need to use the positive value because marginal error is a distance and distance is never negative. So you're gonna use the positive value here. So how can we find this value, ZC here? So we know that the probability in the middle is 95%, right? And it's actually the middle part of the distribution is 95%. And due to the symmetrical probabilities of a normal distributions, you know that the area to the left, to the right of this point should be 2.5. And the area to the left of this point is 2.5 because the sum of these two areas here should be 5%. Okay. If we know the area to the right or to the left here, we can just find ZC using the Z table. (0.025). Right here, right? So 1.96 is a Z value. It's negative 1.96 is a value on the left here. So then the value on the right should be positive 1.96. And then you can just plug 1.96. Sigma is 5.2 divided by 30. Okay. Now go to the second part, or the second example here. When C is 90, sigma is 2.9, and n is 50, n is at least 30, samples is randomly selected, sigma is known, so we can go ahead and use this formula to find the marginal error. Should be ZC times sigma divided by square root of n. ZC, what is ZC in this case when C equals to 0.9? 0.9, that means the middle area is about 90%. If the middle area is about 90%, then the area to the left and area to the right here is about 0.05, right? Because the total error should be 0.1. So what are ZC here? We can go to the Z table now. The number is 0.05. And remember that we talked about this. So 0.05 is this area, and it's going to be the average of these two values. So it was 1.645. So you say 1.645 times 2.9 divided by square root of 50. All right, so we just need to calculate these calculations, and we have a marginal error given a level of confidence, given that the population standard deviation is known, and also the sample size is at least 30, or the populations is normally distributed. Once you find the marginal error E, then you can use the sample mean and the marginal error to construct confidence interval for a given level of confidence. Okay. So by definitions, a C confidence interval for population mean mu is given using this formula here. So mu here is a population parameter, or the mean of the population mean that we're estimating. X bar minus E is the lower bound of the confidence interval. X bar plus E is the upper bound of the confidence interval. So the probability that the confidence interval contains mu is C. So C is a confidence level, is a probability, right? Assuming that the estimation process again is repeated a large number of times, not just one time, but a large number of times. So given this formula here, if you found X bar, okay, so X bar, this is a confidence interval that you are constructing, and X bar should be the point in the middle, and the lower bound X minus E, X bar minus E is the lower bound, and X bar plus E is the upper bound, right? And again, you're constructing this confidence interval hoping that mu, this is mu right here, hoping that the population mean is somewhere in this interval. Again, hoping with a C, right? Probabilities of C that the confidence interval will capture the mean, with the assumptions that this process, this estimating process, capturing the mean of the population process, is repeated a large number of times. Let's do a quick example. A government agency reports a confidence interval of 26.2 to 30.1 when estimating the mean commute time in minutes for the population of workers in a city. Find the estimated margin of error and then find the sample mean. So if you're given a confidence interval 26.2 and 30.1. So 30.1 is the upper bound and 26.2 is a lower bound, right? And you know that by the definitions, 26.2 should be equals to X bar minus E, and 30.1 should be equals to X bar plus E. And X bar should be the point in the middle of this interval. So if we know that X bar is the point in the middle of this interval, we can find X bar because we know that X bar equals to 26.2 plus 30.1 divided by 2, if X bar is a middle point. And then and once we found X bar, then we can find the marginal error E easily. .15 is X bar. Okay. So, and then we know that X bar minus E equals to 26.2. Then E equals to X bar minus 26.2. Equals to 28.15 minus 26.2, which is equals to 1.95. And the unit for this for the sample mean, it should be minutes, right? And also the marginal error is also minutes. So in summary, this government agencies collected a sample, right, of workers in a city, asked for their commute time. And the sample mean that they found was about 26.15 minutes. And then using a certain level of confidence, they found that the marginal error for this estimations is about 1.95 minutes. So they say they allowing their errors, like the sample errors, within 1.95 minutes. It could be higher, it could be lower than the sample mean. All right. So how to construct a confidence interval for a population mean? So before we try to construct a confidence interval, we need to verify some of the conditions. So the first conditions is sigma. In this case, sigma is known, right? The samples is random. Either the population is normally distributed or the sample size is 30, at least 30. So the reason for the sample size is at least 30 is if the sample size is at least 30 by the central limit theorem, the sampling distributions is normally distributed. And you can use the sample mean to estimate the population mean. Okay. And the next step is you're going to find sample statistic n and X bar. So where n is the sample size and X bar is just the sample mean. And the next step is find the critical value, ZC, that corresponds to a given level of confidence, right? You find the critical values, ZC, that corresponds to the level of confidence, C. And then the next things is you can find, once you have ZC, once you have sigma and n, you can find the marginal error. Once you have the marginal error, you just need to subtract marginal error from the sample mean for the lower bound, and you add the marginal error to the sample mean to get an upper bound for your confidence interval. And once you construct a confidence interval, then you can try to interpret that confidence interval. So the interpretations of confidence intervals is quite not simple as you initially think. So let's say if you construct a 95% confidence interval for the population mean, how do we explain that interval to others people? So keep in mind that the 95%, right, or C equals to 0.95 is a probability, right, of selecting a sample statistics that lie within 1.96. standard deviations away from the mean of the sample distribution. So 1.96 here is a critical value that we found for the level of confidence of 0.95. So then the confidence level 95% represent the probabilities of the population mean is captured in a pool large number of confidence intervals of the same size. Okay. A confidence interval that was constructed from samples of the same size, so the large number of samples of the same size that are selected. More specifically, if we selected 100 samples, and we can get 100 sample means, using one level of confidence, you can construct 100 confidence intervals with the same confidence interval, right? And then you hope that 95% of this 100 confidence interval will capture the population mean. Okay. Again, you have 100 samples, you collect 100 samples of the same size, you construct 100 confidence interval. The 95%, then you will say, then is this correct to say that hopefully 95% of these 100 confidence intervals will capture the population mean. But please know that regardless what statistics we find, the population means that we're trying to estimate still remain unknown. So we always try to collect a sample to estimate a population mean, but in real life, realistically, the population mean is still remain unknown. We hope to capture 95% confidence that we capture the population mean, 99% confident that we will capture the population mean. But do we really know whether we capture the population mean? No, we don't. All right. So let's do a simulations. So I'm going to do these two simulations that illustrate how do we interpret our confidence interval in the correct way, right? Again, the confidence interval or the probability that you hopefully to capture the population parameter using a large numbers of samples and a large numbers of confidence interval. So here is a simulation. First, the simulations for a population mean, right? With the normal populations, the mean is about 50, standard deviation is 10, with sigma is known, which means you know the population standard deviations. If the sample size is 10, right, a sample size n is 10, and I select 100 samples, and then I will construct 100 intervals. See how many intervals out of the 100 intervals capture the real population mean. Again, this is a simulation. This is not a real experiment. Because in real life, we have no idea what is a population, what the population meaning. But when we do a simulation, we assume that the population mean is around 50. Okay, and you can see that each of this horizontal bar here, you have 100 horizontal bars, and each bar represents a confidence interval. And in each bar, you have a green dot, right? And this green dot here is a sample mean, is the mean of each of the sample. And the left point here is a lower bound of a confidence interval, and the right bound here, point here, is an upper bound of a confidence interval. Again, we have 100 confidence intervals. How many of them capture the population mean? Around 95% of this confidence interval actually capture the population mean, which is this vertical bar. This black vertical bar represents the population mean is around 50. And 95 out of the 100 confidence intervals contain this population mean. 5 of them miss the population mean. So imagine if you just go out and collect one sample of, let's say, 30 students and ask for their commute time. Your sample can be one of these samples right here. Maybe your sample will capture the population mean, but 95% of the time, your sample will miss the population mean. Okay, if you only collect one sample, it's really hard to say whether or not your confidence interval capture the population mean. But if you collect 100 samples, random samples with the same size, and you calculate 100 confidence intervals, then you can say that 95 out of 100 confidence interval would capture the population means. Okay. Well, again, this is a simulations for confidence interval for a mean when the sample size is 10. What happens when I increase my sample size to 100? So I'm collecting 100 students for my sample instead of just 10 students here. And I still have the same mean is 50, standard deviation is 10, and sigma is known. I will construct 100 confidence intervals. And in these simulations, around 94 confidence interval contain the population mean. 6 of the confidence interval missed the population mean. Okay. With the same level of confidence, which is 0.95. All right, about 90%, not exactly 90. Sometimes you have more than 95%. Sometimes you will have less than 95%. Okay, so the number of confidence intervals that capture the population mean are around 95%. However, as you can see that the width of most of the confidence intervals are much narrower compared to the width of all the confidence interval when the sample size is 10. Again, when you look at the width of each of the confidence interval is much bigger here compared to the width here. And the reason is because when I increase my sample size, I decreases my margin of error. Remember, the margin of error is calculated using the standard deviations divided by square root of n. So if n increases, then E decreases because n is in the denominator. Okay, those are the two points that I want to point out here, which is one, level of confidence is about the probabilities of your confidence interval capturing the populations, assuming that you will be taking a large number of samples. Second, the width of your confidence interval will decrease if you increase the sample size. Okay, that means the bigger of the sample size, the better of your estimations, right? Because when you have a narrow confidence interval, you are more likely to the sample error you reduced when the width of your confidence interval is narrower, your sample error is reduced. And again, our goal, right? You always have a goal of reducing your sample error. The chance of capturing the population mean are the same, but the sample error once you capture the population mean is smaller if the sample size is bigger. All right, let's do a couple of examples on how to construct confidence interval for given informations. Okay. So level of confidence is 90, 0.9, X bar 12.3, sigma 0.8, and is 82. Seems like all the conditions are satisfied. Sigma is known and is at least 30, assuming that samples are random. So then before we can construct confidence interval, we need to find E, right? E is equals to the critical value times sigma divided by square root of n. The critical values for 90, we found it up here, which is 1.645. Multiply by 0.8 divided by square root of 82, which is around 0.145. Okay. And then, well, since the sample means is routed to 1 decimal place, so I wanted to round this marginal error to 1 decimal place. The 1 decimal place, so it should be 0.15. Okay. And then the confidence interval, this is a confidence interval of C equals to 0.9 is, it's gonna be X bar minus E, right? X bar is 12.3 minus E is 0.15 and 12.3 plus 0.15. It's gonna be 12.15 and 12.45. So this is the confidence interval of 90% or 0.9. All right. The second one, C is 0.99, X bar, sigma, and N. So it seems like all the conditions satisfy, so we can go ahead and use this formula to find E. C is 0.99, we need to find the critical values that correspond to 0.99. So if 0.99, which is 99% in the middle, then there's only 1% on the left tail and 1% like on the right tail. So then if it's 1%, that means divided by half, you have 0.05. And it's also 0.005 here. And the goal is we just need to find the Z, right? That corresponds to these two values. 0.005, that should be around here. So you have these two values here, right? And then these two values here has a very close to each other. The difference is 0.000, 0.0006 and 0.0008. Very, very small. That's why we need to take the average of these two values. The average of 2.57 and 2.58, which is 2.57. All right, 2.5 2.575. Which is the z value for 0.99. Times 2.14 divided by square root of n, which is 45. Equals to one decimal place, 0.8. Okay, so once you have E, then you can find the level of confidence. Confidence interval for C equals 0.99 is 10.5 minus 0.8 and 10.5 plus 0.8. (9.7) and 11.3, which is the confidence level of C equals to 0.99 equals to this. All right, let's do another example. Gold prices. From a random sample of 48 business days from January 4th, 2010 through February 24th, 2017. The US gold price had a mean of $1,368.48. Assume the population standard deviations is 2.2, $202.60. Construct confidence, 90% confidence interval for the population mean. First, we need to verify all the conditions. Are the samples, is the samples random? Yes. Okay. 48 business days, that means n equals 48, so it's at least 30. Yes. The population standard deviations is known? Yes. Sigma is 0.60. So all the conditions satisfy, that means we can go ahead and construct and find the marginal error. For 90% confidence interval, we remember that ZC is 1.645, sigma is 202.60, and square root of n is 48. Then the confidence interval for C equals to 0.9, right? Is 15.948 minus 1368.48 plus 48.110. Just give you 13.20, 38 cents, and $14.16 and 58 cents. So this is the confidence interval that we just constructed. This again, this is 90%, right? 0.90 confidence interval. Okay. How about a 95% confidence interval? So we do the same thing. We just need to find E, which is this time for 95%, the ZC is 1.96. And you multiply to 202.60 square root of 48. And you get 1.96 times about 57.32 dollars. Okay. And then the 95% confidence interval, or 0.95 confidence interval, is going to be equals to 1368.48 minus 32, 1311, 16 cents, and 1425.80 cents. Okay, so this is the confidence interval for 95%. And then the next question is just going to compare the width of the confidence of the two confidence interval that we just found here. So let's rewrite them. So confidence interval for 90% is the width of this confidence interval is 14, 16. So the width is just 2 times of the error, and it's 96.20. And the CI 95 width is gonna be just times 2, 114 and 64. And you can see that the width of the 95% is bigger than the width of the 90%. Is because if you're using 95%, that means you have a better confidence interval of capturing the population mean, right? And then if the width of the intervals is bigger, means you have a better chance of capturing the population parameter. So if you increase the confidence level, that is when you increase the chance, right, of capturing the population mean. That equivalents to the wider of the width of your confidence interval. Okay. All right, now we just learned how to construct confidence interval for a different level of confidence. And what about when you have a given confidence interval, right? And you have a margin of error in mind, which means when you're trying to estimate your population parameter, you come up with a given margin of error. So you set your margin of error to be a specific value. So first you set your confidence interval. Second, you set your margin of error to be a specific value within your desired sample error. Right? You have a desired sample error. Then the next thing you want to do is, in order to achieve that sample error, in order to achieve that margin of error, how big of the sample size that you need to collect. Okay. And then using the formula earlier, when E equals to ZC sigma divided by square root of N, you can solve for N to be equals to ZC times sigma divided by E N square. So you can solve for N, right? And once you solve for N, once you know the confidence level, once you know your desired marginal error, once you know the population standard deviations, then you can estimate the sample size for achieving that marginal error with a given confidence level. Okay. A couple of things that you want to keep in mind, that N, if after your calculations, if N is not a whole number, then you want to round N up to the next whole number. Okay. If it's not a whole number, then you round it to the next whole number. If it's a whole number, you can just keep it. The reason why we want to round it up to the next whole number, because in statistics, if you have to choose in between smaller sample size and bigger sample size, you always want to go for a bigger sample size to have a smaller margin of error to achieve your desired margin of error, right? Your desired margin of error. All right. Also, when sigma is unknown, you can estimate it using S, which is the sample standard deviation, the standard deviation that you get from your sample, provided that you have a random sample with at least 30 members, right? So when you don't know sigma, you can use S, which is the sample standard deviations, with the assumption that the minimum sample size should have at least 30. Okay, should be at least 30. All right, so let's do a couple of examples. Determine the minimum sample size, again, is minimum sample size needed to estimate mu, which is the population parameter. For the values of C, which is the level of confidence, sigma is the population standard deviations, and E, which is your desired marginal error. So we know N, well, using this formula here, ZC times sigma divided by E R squared. When C is 90, Z is 1.645 times sigma is 6.8 divided by E, which is 1, and R squared. 645 times 6.8 divided by 1 and square, which give you 125.12, right? Or 13. Then you have to round it to 126. Always round it up to the next whole number if it's not a whole number. So the minimum size should be 126. Again, for the second problem, when C is 0.98, sigma is 10.1, E is 2, then N, the minimum sample size N, should be ZC times sigma divided by E, R squared. Now we need to find what is ZC here. That corresponds to 98.98. And if you draw normal distributions, if you know that 98% is the probabilities in the middle, then the percentage on the right and on the left tells here should be 0.01, right? 1%, 1% is 2%. Well, if we know that 0.01, then we can go to the Z table to find that value, 0.01. 0.00990 here is the closest value. So the Z value for 0.01 is 2.33. So 2.33. is the critical value. So it's going to be 2.33 times 10.1 divided by 2 r squared. It's going to be 138.45. Again, it's not a whole number, then you have to round it up to the next whole number. So the answer for this question is the minimum size, sample size, n has to be 139. You are welcome to collect a bigger sample size, but this is the minimum size that you need to collect in order to achieve this margin of errors with these confidence intervals. All right. Next example, tennis balls. A tennis ball manufacturer wants to estimate the mean circumference of tennis balls within 0.0 inch. Okay, they want to estimate, right, the mean circumference of all the tennis balls to be within 0.05 inch. So if we read this first sentence, we know that the desire of the marginal error that this company is setting is 0.05. Assume the populations, right, is normally distributed. That means we can go ahead and use the z value. Determine the minimum sample size required to construct 99% confidence interval for the population mean. Assume the population standard deviation is 0.1 inch. So we know sigma is 0.1. We know C is 0.9, right? Okay. And the population is normally distributed. Sigma is known. Sample is random. Then we can go ahead and construct a 99% confidence interval. We can go ahead and find the minimum sample size. And again, sample size equals n equals zc sigma divided by e r squared. What is zc for 99%? 0.005. I think we found it earlier that it should be 0.575. 0.575 is the z-score. 2.575 times sigma is 0.1 divided by e, which is 0.05, and square. So it's about 26.5. So, and you would round it up to 27. So you need to select a samples of at least 27 bars in order to estimate the mean circumferences within 0.05 inch. So the second part of this example is, if you given the sample mean is 8.3 inches sample mean. So a sample mean, that means is x bar is 8.3 inches. With a sample size of 34, so n equals 34. 99 level of confidence, 99% level of confidence. So C is 0.99. Oh, this is 99. Then, and a population standard deviation is 0.1. Again, sigma is still 0.1. This is possible that the population mean could be exactly 8.258 inches. So the question is, could the population mean, mu, equals to exact 8.258 inches. How to answer this question? So in order to answer these questions, we need to calculate the confidence interval. And if the confidence interval contain this value, that means it's possible, right? If the confidence interval does not contain this value, that means it's not possible for the population mean to be exact 8.258. Well, let's construct a confidence interval. So E, first we need to find E, ZC, sigma square root n. ZC, we found it here is 2.575 for 99% confidence interval. Sigma 0.1, and now is square root of 34. Which is 0.044. I rounded to 3 decimal places because the value that we're looking at is 3 decimal places, okay? Then 99% confidence interval is, it's gonna be 8.3 minus 0.044, 8.256. $8.344. Okay. Now my 99% confidence interval is in between 8.256 and 8.344. Let me draw it out. 8.256 go to 8.344, and the X bar is 8.3, which means this confidence interval does capture this value, 8.258. 8.258. That means, yes, it's possible that the population mean could be, yes, it is possible that the population mean and population mean here is just the circumference of tennis balls, right? The mean of the circumference of all the tennis balls. Of the tennis ball to be the population mean, which is the mean of the tennis ball circumference, could be exactly 8.258 inches. Because 8.258 is in the 99% confidence interval. All right, so you found the confidence interval. And since the confidence interval does contain the values that you are trying to estimating, right? You're wondering whether or not the population mean could be exact, could be exactly that value. Then you can conclude that yes, it's possible that the population mean is exactly could be exactly 8.258. Could be. Again, we use statistics, we use samples to estimate the population mean. We hopefully that we can capture the population mean, but realistically, we have no idea whether or not the confidence interval that you constructed actually captures the real value of the population mean, because the real value of the population mean is still remain unknown. All right, so this lecture introduces the idea of confidence interval, right? How to construct confidence interval in order to estimate your population mean, and how to interpret your confidence interval in terms of probabilities of collecting a large number of samples, and how to estimate the minimum size of a samples in order to achieve a preset margin of error or a desired margin of error that you want to set for your analysis.